Chapter 5, Section 1, Formative Assessment. The first question, who is credited with developing a method that led to the determination of standard relative mass? So, before the periodic table has its present form, in the early days, there are people who are considered as pioneers or icebreaker for arranging elements. So, but different arrangements were made by different people. So, in order to come to one single standard approach, the first person who is credited to develop a method that leads to the determination of standard relative atomic mass is the so-called Cannizzaro. So 1A is Cannizzaro. 1A Cannizzaro. So this is double N, Cannizzaro. Cannizzaro. And 1B, who discovered the periodic law? Mendeleev, of course, who is the father of periodic table. Mendeleev. Dmitry Mendeleev, who the Russian the scientist who applied standard atomic mass after having a meeting in Germany. Cannizzaro, based on Cannizzaro's comment, he make use of atomic mass to arrange elements in the periodic table. So, Mendeleev discovered the periodic law. And the third one is 1C, who established atomic number as the basis for organizing the periodic table. It's Henry Moseley. Henry Moseley tried to use apply emission spectra after thoroughly investigating the emission spectra. He come up with a pattern that arrange elements based on their atomic nuclear charge, which means proton number. So atomic number is selected. So with this, the periodic table uses atomic number. So periodicity, the definition of periodicity according to Mendeleev, bases on atomic mass, but this one is atomic number. State the periodic law. The periodic law is stated as follows: the physical and chemical properties, the physical and chemical properties of the elements are periodic functions of their atomic numbers. So this is the periodic law. The physical and chemical properties of the elements are periodic function of their atomic number. So after a periodic interval, we will see in the periodic table elements are arranged in one group having similar chemical and physical property. So this is the second one, and the third one we have to push a little bit this one up. According to the third question, name 3 sets of elements that have been added to the periodic table since Mendeleev's time. So Mendeleev hasn't noticed the following groups, like the first one is the first group is noble gases, and the second group are lanthanides, the lanthanides, and the third group is the actinides, so if you see the present periodic table, it has this form. It's roughly sketched, actually. We better sketch it a little bit. At least it should look like present periodic table. So we have these group 1 and group 2 and group so this group 18, the noble gas, here is a noble gas. This is noble gas, and another is the actinides and lanthanides. The two parts, these are lanthanides, and these are actinides. These are the 3 parts that have been added to the periodic table since Mendeleev's time. So the third question is this one. The fourth one, how do the atomic number of the elements within each group 1, 2, and 13, 18, according to main period, 1318 means 3a. So the periodic form is given in 2 ways. This with, let's say, if we are considering 1a, 2a, it becomes here 3a, then up to 8a. But if we are not referring, if we are referring the D block as well, which is the transition elements, we start from 1a, 2a, 3a. No, we have to remove a and simply count 1, 2, 3, 4, 5, 6, then 12 is here, then 13 comes, 13, 14, 15, then we stop at 18. But so now we are 2 ways. If the element is in representative elements, which is if the element is in S block or in P block, we can make use of this one, 1a, 2a, 3a, 4a. Otherwise, we use this arrangement skill, then subtract 10 from the group number. So in group 1, 2, and 18, the difference between in groups 1, 2, and 18, the differences between the atomic numbers, of successive elements are 8, 18, 18, 18, and 32, respectively. In groups 13 to 17, 13 to 17. The differences are the differences are 8, 18, 18 and 32 respectively. So how do the atomic number of the elements within each of group 1, 2 and 13 to 18 of the periodic table vary? In groups 1, 2 and 18, the difference between the atomic numbers of successive elements are 8, 18, 18, 18, 32. In groups 13 to 17, 8, 18, 18 and 32. Next one is 5. Question number 5. Why are elements' atomic mass not in strict increasing order in the periodic table, even though the properties of the elements are similar? For example, by atomic mass, tellurium, this one, should be in group 17 and iodine should be in group 16. So if we see the property, tellurium is in the same, with its present order, it is assigned with the correct order, the correct behavior. It's assigned with elements having similar property with tellurium. But there is a discrepancy between atomic mass. So here iodine has got lower mass, so it should come before tellurium. So what is the reason for this? But grouping the properties. So this is all about isotopes, because in Mendeleev's time, the assumption for isotope was not there. So arranging elements using atomic mass has one of the drawback is atomic mass is the average mass. We have to make the average, which means two elements having the same representation but different in mass. So isotope consideration must be there. So an element that had the atomic number, atomic mass, is a weighted average of all of the naturally occurring isotopes. So the answer for this 5, atomic mass is a weighted average weighted average of all of the naturally occurring isotopes of an element. So a few elements have a higher atomic mass than does the element one atomic number. when atomic number higher, because those elements have disproportionately disproportionately dispropor dispro disproportionately large heavy isotopes, large heavy isotopes, isotope abundances. Here, the main point of this answer is here. Elements, even though they have the same isotopes of the same element, having different mass, that mass have disproportionately large heavy isotopes abundances. That's why we have instead of increasing continuously at some places, we will see some anomalous behavior. That behavior is because of isotopes. Some isotopes have disproportionately large heavy isotopes abundances. In the first place, atomic mass is a weighted average, because when we consider atomic mass, we should consider the weighted average. So when we take the weighted average, we must consider the abundance. So to see one example, let's say we have an element X isotopes, let's say with atomic mass Z atomic mass, and an element X with Y atomic mass. To find the weighted average, the average of the two, I must know the abundance. Let's say the abundance of this one is 25%, and this one is 75%. So the average value is considered Z times 25% plus Y times 75%. This will give you the weighted average. The weighted average. So now the result for this one to be less than the order, because some of them have got disproportionately large heavy isotopes. So we will discuss in the next lesson about this thing. So these are some of the questions that we consider in this section.